All right, so we'll start then with today's class. And if you recall, we essentially left the last class with having introduced the basic, actually having introduced the radiative transfer equation, but then we took the equilibrium case as a first example here and started to discuss blackbody radiation, equilibrium radiation, introducing Planck's radiation law, spectral shape of it. With the sort of caveat is that we actually just took it for granted for now, and that's what we'll do. We'll work with its properties today and analyzing that. Also coming to the basic definition of a quantity like the effective temperature, for example, which is very often used in astrophysical research, right? And we didn't really specify where it came from. And the reason for that, I mentioned already in the last class, is that we need a little bit more material in order to go there, but we will in the next chapter and see how actually, what the origin of Planck's radiation law really was. We will look at Planck's original derivation even in a sort of form. And for now, we will just take it for granted. So we're going to continue with that exploration now of blackbody radiation. So last class, again, we discussed the various frequency-dependent properties. We looked at the Rayleigh-Jeans limit, the Wien's limit, the full spectral function, and also deriving then Wien's displacement law to actually get a connection, how you can just look at the spectral, a spectra of, say, a star, and just by looking at it, get an immediate feeling for what the surface temperature of that star is, even though it doesn't radiate like a perfect black body. All of that we handled. Today, we're going to look at the, we can call it the integrated properties of the blackbody radiation law and what they can teach us, particularly about the various radiation quantities that we introduced in the previous chapter. Now, what do I actually mean by that? Well, I just mean that if you have a given temperature, then the integrated blackbody radiation law is just the Planck function at a given temperature integrated over all frequencies. Okay? Remember, there were no angular dependence in the Planck function. That will come back several times today. It's isotropic. Yeah? So, B nu of t, we know it had this dependence, right? Okay? So, this is actually left for you to do as an exercise. It's an algebraic exercise, not bad to do, okay? It is in the course book. The answer that comes out here is sigma T4 divided by pi, where sigma is the Stefan Boltzmann constant. And part, of course, of the task in the exercise is to see how this is just actually a combination of the fundamental constants that is part of Planck's radiation law. Okay? It is also, of course, given to you, its numerical value, etc., in the course book. The second thing we can just see here is that, okay, for B of t, the integrated properties is proportional to t to the cubed. Yeah? So the integrated value is higher the temperature becomes. So, all right, now let's connect this then now to some of the radiation quantities that we have introduced in the previous chapter. We start with the energy density. So the radiation energy density, we know, is just 1 over c integral over all angles, integral over all frequencies of the specific intensity, I nu, and then d nu, d omega. But now we have said that the specific intensity is given by the Planck function, b nu, and b nu is angle independent. That is, it's isotropic. It doesn't contain anything there, right? So actually, we can just separate these integrals then and get this. I'm going to do an extra step here just for clarity, right? This is now as a function of t, of course, yeah? But, well, the first one we have done, that's 4 pi, so 4 pi divided by c. The second one we just gave down there. It's just this one. So this becomes just 4 sigma divided by c T4, which you often see as A T4, where A then, of course, is equal to 4 sigma divided by c, and it's typically called the radiation constant. That's just unfortunate because, you know, we have more letters to keep in our head, and A is not such an original letter. Anyway, but that's how it is. That is the radiation constant, and this is then the energy density for given temperature T of blackbody radiation. You can see, interestingly, it depends on temperature, but not on the material density, for example. Now, connected to this, I wanted to do a little detour before we move on to the other quantities that we have discussed, and that was that I will allude again to what we will come back to later in the course, and that was that, okay, what if now, instead of using the full black body radiation, we just use the Rayleigh jeans part, okay? That was the classical part I already said, right? Well, if you remember what we had then, this comes out, it was also isotropic, but this would be something, well, we can just do it here, right? We needed to Taylor expand this in the limit that h nu divided by kt was much, much smaller than 1, with the 1 Taylor expansion that we need to have in our head throughout this course. And then we saw that this becomes 2 nu squared. You get a k, you get a t, you get a c squared. H vanished, of course, Planck's constant. Yeah? And then the nu. But the thing is here that this contains nu squared. Yeah? So what happened to nu squared when you integrate from nu 0 to infinity? This goes to infinity independent of the temperature. And this was why it was called the ultraviolet catastrophe. It was already known that there need to be this some sort of cutoff that we discussed in the previous class at high frequencies, because otherwise the energy density of any given black body radiator would be infinite, which is, of course, absurd. So people knew there was something wrong. Right? That being said, this is a very useful law to use when this condition is fulfilled. Often, for example, in radio astronomy, which we will come back to. All right. That was the energy density of the black body radiation. Now we're going to look at flux. So, the flux, well, we know that black body radiation is angle independent, right? So, previously, remember we did the calculation that if we had this, I knew of theta and not of the second angle phi, then we already knew that if we put this in a Cartesian system, then we already show that x, fy equals to 0. But in general, the z component was not 0. Now we're going to see what happens when we plug in blackbody radiation in the z component. So we just use that again in its definition. I nu, which now is b nu, so we're just going to replace it by the Planck function. Yeah. Then you have a mu, the nu, the omega. Okay, where mu is the cosine of the angle, as we have seen for the c direction of the flux. This is also then what we typically call the flux, as discussed. So again, though, b nu is not a function of phi, no, but it's also not a function of theta. That is, it's not a function of mu equals cosine theta. So we can again take that, separate the integrals. Oh, holy moly. We get this out, and it was, what was it? It was sigma T4 divided by pi, right? And then we have a 2 pi from the phi part, and then we had mu minus 1 to 1, yeah? Mu, the mu, okay. But here we had this little nice integral. We have an uneven integral on an even interval, which is just 0 always. So indeed, we already sort of knew this, but the flux from a black body, isotropic radiation field, is 0. Indeed, when the radiation field is isotropic, we show that the flux, per definition, must be 0. You have everything, contributions, think about it as your rays of light, contributions from all different directions, so that the net effect in all directions cancel out. It is 0. All right. Now, we're going to look at the third interesting quantity that we have discussed. What was that? Right, that was the pressure tensor. And remember, again, if we make this approximation, it's only a function of theta first. Okay? Then we already showed that it had the following form: 1/2 E minus P, 1/2 E minus P, P, where P now equals PCC, the radiation pressure, analogous to the flux. Okay, so let's evaluate. E, we have already evaluated. I took it away from the blackboard. Let's hope we remember it. PCC remains. Okay. We have a blackbody radiator. We have 2 cosines theta now, if you remember. So mu squared, yeah. The nu, the omega. So that's then, again, by analogy, this has no mu dependence in it either. There is a 1/c missing here. Yes, sir. 4 pi divided by c. No. Apologize. First, this one. We have the 1/c. I'm going to do this. Sigma T4 divided by pi. Yeah. 2 pi comes out from the pi integral, and then you have mu from -1 to 1 mu squared d mu. Now, this is no longer an uneven integral. It's an even moment of the radiation field. So this doesn't cancel anymore. Instead, if you evaluate this, it's just mu cubed by 3, right? So what comes out is 2/3. So you have 4 pi 3c sigma T4 divided by pi. Haha, but then we realize that this is actually just E divided by 3, which we sort of knew since it's an isotropic radiation field, that 3 times the pressure, if we use that notation, has to be the energy density. So let's plug that into our tensor here. Well, then you see that indeed you get a diagonal tensor where the value is just the value of that. This is what we call the isotropic pressure, isotropic radiation pressure in this case. All right. So now we're going to use these properties that we have verified. The blackbody radiator. I'm going to talk about some common definitions and astrophysical examples where this is useful. So we're going to start with like sort of a definition of what is called Teff, or the effective temperature. So in your Intro to Astronomy course, you might have seen a so-called Hertzsprung-Russell diagram, which goes something like this and something like this, with the intuitive leftward axis here. And if you put it not on a color magnitude, which is the observational equivalent, then you have something like the luminosity of the star there and the effective temperature of the star there. Yeah? And then, you know, you put your main sequence. Most stars live along there. The sun is around here somewhere. The hot massive stars that me and Frank works on are up there. Here are the supergiants. Here are the white dwarfs, and so forth. Right? But this is Teff on that. So what's that? Now, you might have heard, definition of Teff is just the effective temperature is just the flux that the star emitted if it were a black body. But now you should immediately be a little bit suspicious, huh? Oh, but you just showed us 2 minutes ago that the flux from a black body was 0. So what's that all about? Well, the thing is that we have to, again, remind ourselves of something we did the first week, okay? You look at the surface of an object now. Here. I'm going to just sketch this. As a surface, okay? Now, of course, deep inside that body, you know, you might have radiation coming from almost all directions, such that if the radiation behaved like a black body, then the flux would be 0, right? Now, the definition of Teff, though, uses another thing, and that is that, okay, what if we now have emission only, well, say from a star in the upward direction from this surface, and that emission were as a black body, okay? So that means that you have something, and that could be what you calculate in your model, or it could be what you measure. Yeah? That is then the, well, it's 2 pi, right? Because the phi integral has already gone away. And then it's mu minus 1 to 1. It's nu 0 to infinity, okay? Specific intensity, I nu. And then you have a mu d nu d mu. The other way around. Okay. So the whole idea here now is that, well, at the surface of the object, as we discussed last week, you actually don't have any incoming radiation. Imagine the plane here, and then stuff is only radiating in this direction, in the outward direction. There is no incoming radiation here because it's the surface of the object. Okay? So that means that all angles, if you put it in this format, that goes from there and then all inward angles, they do not have any radiation. Right? So the only thing that contributes, if you want to calculate then the flux from in this direction, are the angles in the outward direction, given then by the theta angle there, yeah? So that mu equals to cos theta here again. And then, of course, in the general sense, you have to integrate over all the mu angles like this. Yeah, we have already taken that 2 pi integral out, assuming that. But there is no incoming, which means that all angles from there to there is no contribution. So the radiation field then is not isotropic. It might have the same spectral shape as the black body, yeah, and that's what the definition of Teff is actually based on, but it's no longer isotropic. Okay? So you can, like we did, you can go back to the first week of classes and see when we did this in the generic context, right? Then the angles from -1 to 0, well, they all have intensity that is 0, so they don't contribute to the integral. So the integral then is just 2 pi. Mu goes from 0 to 1. All frequencies, I nu, mu, d nu, d mu. Okay. And then we're going to leave a little wiggle room there, yeah, to discuss. But we're going to say, okay, what if we now say that the specific intensity is the Planck function? Well, then no longer, we don't have the full integral here. We're only considering from 0, right? So it's not going to cancel anymore. So then Fc becomes 2 pi. This is then, again, the integral over the Planck function. Yeah? So that's sigma par divided by pi. And then we have that integral, which is just now mu from 0 to 1 over mu. So that's just 1/2. Okay? So what you can see happen now is that these cancel. This is just sigma T4. Okay? In the case of a black body. And that's where the definition of Teff actually comes from. So now we can say that, okay, in the generic case, we have some sort of specific intensity here, yeah, at the surface of the objects, and then we can assume that it's free streaming to us, so perhaps we measure it, yeah, or perhaps we measure the flux from the object, right, depending on if we can resolve it or not. And then we're doing that in some sort of frequency band, okay? And then we're using some sort of technique to estimate those that we do not observe. Alternatively, you can think about, okay, I'm going to compute a model on how the specific intensity interact with the material down here, and then how much is actually escaping the surface. And then I'm going to calculate that. And then typically that involves solving this radiative transfer equation that we introduced, and we will talk about much more during the rest of this week. And that's normally then gives a specific intensity, which might have an angle dependent, which it typically does, and it might be very frequency dependent. Might also deviate from the black body in the frequency dependent, in the frequency dependent quantity. Okay? And then we measure the flux from that, we calculate or measure the flux from that, and then a value comes out. Okay. And then perhaps we get out a very, a value like, I don't know, that is 10 to the minus 12. I'm just making a number up now, right? And that's like, okay, what does that mean? Well, it's very difficult. So a convenient way to then say this instead is that, okay, we're going to define this as sigma Teff 4, which then uses this relation, which was derived for if it were a black body, emitting only in the positive. Yeah? But it's not necessarily that it has to be the black body. Okay, now, then we have that definition of the effective temperature. So, the correlation with the effective temperature and the actual then temperature of the object, of course, depends on how well can you approximate this emitting surface as a black body. And that can be very different for different situations, right? For example, if you now take a stellar atmosphere, so a star, okay, then the emission layers from the star are centered around what we call the photosphere. And we will discuss how we can define that in just a minute. But then, if you set up the most simplest model for such a stellar atmosphere that you can, which we will do later on in the chapter, then you will find that the effective temperature, or the flux temperature, of the star actually equals the temperature at an optical depth of 2/3. The optical depth we will formally introduce after the break today, but it's a measurement of how far into the object you can see, how transparent or opaque is the object. So for example, when I look outside today, I can see the building behind us. That means that the air between me to the building is kind of transparent. If it were a foggy day, perhaps I wouldn't be able to see it. Then you would only see the fog. Now, if that were the case, I could say that I am in optically thick conditions. I do not see the underlying source, which in this case is the building, because it is obscured. The light that is gathered from that building to my eyes is obscured by the intervening material, which is optically thick. Today, the material in between me and the house is very optically thin, transparent. The optical depth is not very high. I can see it, okay? And the transition between being optically thin and optically thick is on the order of 2/3 or 1. Really, it's more of a function, because some photons will escape from optical depths of 2/3, some from 1, some from 2, etc., etc. On average, it's on the order of unity. And this is then why, in a star, for example, the effective temperature is related to the actual surface temperature of the star, because from these layers, the light is emitted, is vanishing to outer space, and we're seeing those. Okay? Again, this now is also a way to define what we call the surface of the star. It's a gaseous object, so it doesn't really have a solid surface like here, right? So we have to define it in somewhere. And often this is defined at the layer where the optical depth is 2/3. But this also means that it's different for different wavelengths. We haven't come to this, but the optical depth involves a wavelength dependence. I didn't do that here, or frequency dependence. And this means, for example, that in the optical light, visible light here, the star looks a certain size. We define the photosphere of it to be on the order of tau 2/3 in the optical. But if we look in the radio wavelength, then the size is different, because the optical depth is different there. And we'll come back to that. Okay? So that's a first connection there. Now, a second situation, there are many situations, I will just take a few, is if you have like an accretion disk around, say, a supermassive black hole, yeah? Then under certain circumstances, this could be approximated, and this is something that you will do more with me if you are in the master's program after Christmas, when we do galaxies and cosmology. Yeah? We'll just mention a little bit, and we will do more accretion and supermassive black holes and all of those things. Now, if you have here, okay, a little emission area, and then you say that this disk is geometrically thin, it's very thin in the vertical direction, but it's optically thick. And then you approximate it as a black body, you get the same, right? Then you get that it's emitting in that direction and in that direction, and that the flux that is emitted is indeed sigma T4, according to the same ID. Now, important here is that the luminosity, right? The luminosity of the object is the radiative energy output per second, also called the power. That's the area times the flux. Flux was energy per second per unit area. So for a star, for example, well, a star is to first approximation spherical, right? So then the luminosity would be 4 pi r squared times the flux. Or if we use this, 4 pi r squared sigma Teff 4, okay? So that's where you see this. But then again, it always becomes a little bit ambiguous, right? Because you say, well, then you have to define the radius of the star. And typically you do this again at an optical depth of 2/3 or something like that. Now for the accretion disk, on the other hand, the luminosity is different. If we're only interested in a little portion here, right? A distance r from the center, yeah? Then, of course, the total emitted area here would be, if this is the area times the flux, would be 2 pi times r times delta r times sigma T4, according to the same. And then we have to multiply by a factor of 2 because we can emit up and down. So the surface area is different, so that's why the expressions for the luminosity becomes different. So that was just 2 examples of how we can use these IDs to connect them to various astrophysical objects. And actually the idea of a photosphere we can extend at an optical depth of 2/3. We can extend even further. We can even talk about, and we shall, about the photosphere of the universe. And that you might have heard about in your Intro to Astronomy course again, called then the era of recombination. Okay, now what actually happens during the era of recombination is something that we will study in some detail, at least, in one key application of the course, 8.1, that we will do later. Yeah? But the thing is that during that era, the optical depth, when we go from today and back in the path, increases drastically, such that you hit essentially an opaque wall. The universe becomes opaque, it becomes optically thick, and that's where the cosmic background radiation photons are emitted that we can see today. Typically, you also refer to this in this context as the surface of last scattering, which again should probably be, like I referred to in the beginning, some sort of, it's more of a cloud, because it's not like it's a complete surface like that. Some photons will emit a little bit higher optical depth, some a little bit lower, okay? And we will come back to that again. And also now, I've talked a lot about optical depth, but I haven't actually said what is this optical depth, and that's something we will do after the break, where we discuss some simple examples of the radiative transfer equation now. Okay.